Hello. Hi. Let me know when you can see and hear me so I know I'm not talking to myself. Hello, hello, hello. Aw, hello. Hi, can you see me? Am I there? Yay. Okay. Amazing. Hello, hello, hello. Okay, we'll be doing an intro, Fatima, so don't worry. Wonderful, I am here. What great. I'm glad that I'm here. There's so okay. Hello, I recognize a few of your names already from summer school, which is fantastic. Hello. Hi, Hepzibah, Taz, Shadid, Tajuddin. I think I recognize your name. Sanjeed, Hannah, Isabel, Rooks, Zar, Satoru, Aisha, Tia. Oh my gosh, so quickly. Kamara, Sammy. Amiko, Evelyn, Zan, Panache, Jamie, Mercy, Lamisa. I do. Mariam, Adam. Hi, Omid. Hello, hello. Donald, Fatima. Oh my God, too many. Charlie, Luca, Adam, Bob, Ellipsis, Ethan, Maya. Hello, Hajira. Don't reply. Okay. Adam, Varali, Ramino, Mariam, Enzo. Okay, I might have to stop now. Otherwise, this might be the whole lesson. But hi. So, hi. Oh, we've got lovely, lots of moderators and mentors in the chat to help us out today, which is fantastic. Make sure that you say hi to them as well, and you make sure that they've got a nice task ahead. Fantastic. Hi, Pranav. Hi. How are all of you lovely year 11 students? If you were in my summer school, can you let me know? Okay, I recognize a few of your names already, but please do remind me. If you're in summer school, let me know. If you're new, then say new so that we can all be extra nice to you. Amazing, lovely. So many of you. Oh, you didn't get a break. It's fine. Well, I'm just going to be giving you like a bit of an intro for the first 5-ish minutes, so your brain can kind of just take a break and listen to my voice. Hopefully, it'll be nice and soothing. I won't speak too loudly, okay? And then that will be your break from maths before we get into the chemistry, okay? Hi, lovely newbies. Hello, and existing summer school. Great. Okay. Lovely Tajuddin, as long as you save it until after. All right. Great. Lovely. Hi, Fatima. So, welcome to the Year 11 Chemistry main course. I'm glad to have you all, whether you are new or existing. Just as a quick rundown, actually, should we do intro? Let's do intro first, so just you know who I am, and then we can start asking. Okay. So, hi. Um, I am LaJoy. That's me over there. Okay. I mean, look, I might as well. Ah. Okay. So I am I'm the head of chemistry at my ed space. So I am, of course, a fully qualified chemistry teacher. They didn't just find me on the street. I have been teaching for 10 years. And I studied chemistry at University of Oxford, and that course was called an undergraduate master's degree. So it's a 4-year course. The first 3 years, you do your labs, you do your lectures, um, you go to your tutorials, and then in your fourth year, you go into a lab and you get to work in a real research group and make some stuff that nobody's made before, which was really, really cool. And I came up with a first. So, yay, I'll just pat myself on the shoulder, seeing as there's nobody here to do it for me. You live in Oxford. Okay, great, lovely. For my A levels, so back in the day, I got 3 A stars. So I did biology, chemistry, and maths for my A levels, and then also did AS. So Tia, that's a good question. So again, back when I did my A levels, it was kind of split into 2 years. So in the first year, you did AS levels, and then at the end of that first year, you then usually dropped one and then carried on with three into the next year to get your A2. So for my AS in year 12, I did biology, chemistry, maths, English literature and French because I used to want to be a lawyer. And then during my A levels, I fell in love more and more with the sciences and chemistry in particular. So at A level, I dropped English literature and French and I stuck with my sciences. So I did biology, chemistry, and maths for A level. And I loved them. Chemistry in particular, and math, I love maths as well. Okay. Biology, I like, but not as much. Okay. Before we start, especially as this is our intro, I'm going to give you a couple of minutes. If you have any questions, ask those questions. I'm going to talk to you a little bit as well about this course. So the way that this course is going to work for year 11 is, first of all, everything is aimed towards higher. So if you're doing the higher course, then this is all the content. If you're doing foundation, then of course, everything that we teach here you'll also find it relevant to you, but there'll of course be some parts that you don't need if you're doing foundation. Okay. This course is for combined and triple. So if you've had biology or physics already, then you might have already heard. For lessons 1, 2, and 3, it's for everybody, so combined, and then the fourth lesson is for triple. Okay, so it goes 1, 2, 3, and then triple, and then 5, 6, 7, and then triple. Okay, so every fourth lesson for combined students, you get that fourth lesson off, right? But for triple, you're here for every single lesson. Okay, so this course, yeah, higher combined. So whether you're doing higher combined or higher triple, this course is for you. If you're doing foundation, then there'll be some things in this course that don't apply to you. So if you know the specification, you'll know which bits you just don't need to know about. Okay. Um, yes. So Fatima, that's a good question. There's actually a site. If you literally Google AQA to, actually no, Edexcel to AQA, you'll see there's a document that tells you exactly which bits are slightly different between the two exam boards. So what you'll find is most of the content, if not like 99% of the content, is exactly the same. The only difference really is that some of the content is in different papers. So some parts that might be in paper 1 for AQA might be in paper 2 for Edexcel. Okay, but in terms of the actual content, and same with OCR, again, all GCSEs are trying to get you ready for A levels, which means that they all need to cover the same base content because you need to know the same stuff to get to A level. Okay, so this course is AQA. But if you're doing other exam boards, you can still follow this course when it comes to the content. It just might be that some of the things that we say in terms of the split for exam papers won't necessarily apply to you. So just make sure that you know your exam paper split and your topics because it will be slightly different if you're not doing AQA. Okay. So Yvette, that's a good question. So how this course will be for chemistry is for the first month, so for September, we'll be doing essentially kind of revision, so reviews of some of the core topics that you most likely learnt in year 9 and or year 10, and you really need to make sure that they are secure before we carry on learning more stuff for year 11. Okay, so you'll see that that's things like, if you look at the timetable, so we'll be doing things like writing equations. Today is structure and bonding because that's so kind of standard, foundational. We'll be doing lots of calculations, so quantitative chemistry, a lot of quantitative chemistry over the next month, acids and bases, ionic equations, redox. So all of those kind of core things that you then need to make sure that you're really confident with the chemistry. And then from October, that's when we'll go into the new content, which is like energetics, rates of reaction, organic chemistry, etc. Okay. Enzo, yes, we will be doing triple content. So every fourth lesson will be just for triple students. And so for this month, again, that fourth lesson, it will be delving into the quantitative stuff that is only for triple. So like concentration with moles and gas volumes. Okay. Yes, if you do single science, yes, you can do this course. It just might be that some things don't apply to you. So whichever exam board you're doing, and yeah, even if you are doing AQA, the exam, what am I trying to say? The specification should be your very, very best friend, okay? You should know the specification inside out and up and down, so you know which bits you need to know and which bits you don't. Okay, triple and combined. Triple, there's just some extra stuff. So if you see things in the specification that say chemistry only, then that's triple. Whereas if it doesn't say chemistry only, it means that that is for everybody. Okay. Same thing when it comes to Edexcel IGCSE, Abdurrahman. So most of the content will be the same. There'll be small bits that are different. If anything, you'll learn too much with this course, okay? Because there's slightly less content in Edexcel in IGCSE than there is with AQA, but the vast majority of it will be the same, okay? Okay. So again, just to recap, first month review of topics that you should have covered already in year 9 and year 10 to make sure that they are really secure. Derek, I don't know the website off the top of my head, but literally if you just Google switching from Edexcel to AQA, it's the first thing that comes up. It's the official AQA website and it tells you everything. Okay? Okay. Any more questions before we get into this lesson? Make sure that you've got your periodic table. Always good to have, okay? 6 teachers for chemistry. Oh my goodness. You'll be okay. If you don't, I know if you don't have a teacher, it's going to be some extra work, but you can still get through it. In my A level, I didn't have a teacher for most of year 12 and a little bit of year 13. And it all, I mean, and look, it's fine. Okay. Your wall is your periodic table. I love to see it, Adam. Okay. Um, oh yes, dynamite. Sorry, yes. So that's a really good question. So, as I said, first month revision, review, recap. Then we get into the new stuff, which will mostly be energetics, rates, reversible reactions, organic chemistry, and chemical analysis. We will be finished that not too far into the year. So by around February, we should then just be doing revision. And so it'll be a lot of exam technique, a lot of practical revision, Tia. So yes, going over the required practicals. So lots, when I tell you, you might get sick of revision. There's going to be so much time for revision. There shouldn't be, by the time you get to your exams, there shouldn't be a past paper question that you haven't seen or a type of past paper question that you haven't practiced. Okay, so we're gonna do it. When it comes to homework, there is homework for every single lesson. It's 5 questions for every lesson, and it's written questions for every lesson. So for summer school, I know it was multiple choice. Okay, we're in year 11 now, so multiple choice is gone. Okay, so written questions of a range of marks. There might be some questions that are literally 1 mark. There'll be some questions that are 6 marks. Okay, and then of course, just like with summer school, there are video solutions to go through for every single homework question as well. And if you're on the pro package, then you've also got your mentor to help you out. Okay, can you bullet point? It depends on the question. Some questions where it relies on quality of written communication, absolutely not. I think to be safe, I typically don't bullet point. I mentally bullet point, right? Like you can write in really succinct sentences that are basically bullet points without drawing the actual circle. Okay. If you did all the lessons as revision, would that be enough? Alex, that's a good question, and it depends. If you're getting, I would say as if you've done every single type of past paper question that exists, then you're prepared. Okay. And not just done them, but marked them, reflected on them, figured out what you're not getting, and then gone back to them. So yes, there's going to be 6 mark of okay. There is going to be so much exam technique practice, you are not going to know what to like. It's going to be like, okay, I get it now. I know how to do my exam. Okay, fine. Okay. So revise and memorize key experiments. That is a very good question. Part of it is kind of mentally picturing yourself doing them. Another part is past paper questions, because when you read through those questions, then you're put back into the kind of investigative mindset. Okay. There aren't lessons in the Christmas holidays, Isabel, but there are Easter revision lessons because that's coming up right to your final exams. Okay, let's get started. All right, let's get into the chemistry. Otherwise, I feel like we could spend this whole time just talking about the course. Exactly. Okay. So those of you that were in summer school, some of this might look familiar, but today, as I mentioned, we're starting on structure and bonding, but we're focusing specifically here on ionic bonding and covalent bonding. Okay, so for ionic bonding, can I have the definition in the chat? How would you define an ionic bond? Okay, think about what ions are. Lovely, blurry, fantastic. Electrostatic. So some of you are just saying metals and non-metals. That's not a definition for a bond. I can't say what's ionic bonding and you say metal and non-metal. Okay. Electrostatic, forces of attraction or force of attraction between oppositely charged ions. Now, typically, when it comes to those oppositely charged ions, the positive ion is usually the metal ion, and the negative ion is typically the non-metal ion. Okay, so that's our ionic bonding. And you're absolutely right, Aisha, it does involve the transfer of electrons. Oh, sorry, this is my shorthand. Instead of writing positive, so positive equals positive. So plus and then VE, like positive. I don't know. I just got used to doing that. Yeah, exactly. Now, something or a tip actually that I want to give you actually straight away, when it comes to your notes, especially because you'll be doing so much work, it is absolutely fine to use like shorthands and like abbreviations. But when it comes to your exam question practice, make sure that you are writing in full sentences and make sure that you are timing yourself, okay? Don't time yourself when you're writing shortened versions of everything. Time yourself when you're writing it fully so you know actually how long things are going to take you. Okay. Ayan, yes, indeed. And we're going to get onto equation writing in our next lesson, which might be my favorite. Okay. Let's have covalent definition, please. Use the metal, the T for hyphen. Okay. Covalent bond sharing of electrons. We need to be more specific than that. Fantastic, Lamisa. Someone was paying attention in summer school. Shared pair of electrons. Okay, and you're right, typically between non-metals, Enzo, it's between the nuclei, oops, of the non-metal atoms. Two atoms share one or more pairs of electrons. The sharing allows each atom to attain a full outer shell of electrons. I agree with you, Abdurrahman. Okay. And you're absolutely right, Ayan. In both cases, it's to allow both atoms to get a full outer shell and therefore be stable. Around when do we do quantitative chemistry? Literally in about 2, 3 lessons time. And we're going to spend a good amount of time on quantitative chemistry. I think we've got like 4 lessons on quantitative. Okay. Let's keep going. Now, remember, when it comes to bonding, that's not the same as the structure. Okay. Now, the type of bonding, it says nuclei, plural. Quantitative is for everybody, but some of the quantitative lessons will be triple only, right? So for everybody, we do mass and moles. and mass concentration, but for triple only, that's when we do mole concentrations and gases. Okay, yes, Ayan, this will be the same across exam boards for bonding. Okay, if you have a look at the timetable again for this first month, it is a review of content that you would have learned from year 9 and year 10, and then we'll start going in a more kind of structured order. Okay, so when it comes to ionic compounds, their structure isn't just one positive ion next to one negative ion. They exist, and some of you have said, oh, Ramino, fantastic. They exist in a giant lattice structure, where a lattice is essentially just your 3D structure with repeating positive and negatively charged ions. Okay. Now, when it comes to melting point, do ionic compounds have high or low melting points? And ideally, why? Fantastic. Fahim, Isabel, high. Why are their melting points high? Excellent. Oh, so I am not into molecular forces. I'm glad that you said intermolecular forces, same Jason, because it's a really common mistake to make. Now, if we think of the word intermolecular, molecular. So we need molecules for intermolecular forces. But ionic compounds don't exist as molecules. Ionic compounds exist as giant lattices. So absolutely high because there are strong electrostatic forces of attraction between the oppositely charged ions. And then a comment on energy. Who mentioned energy? Fantastic. One Piece on top. Okay, sure. I still need to watch that. Therefore, a large amount of energy needed to break these bonds or overcome these forces. Ooh, that is a good question. Wind Ninja Soul, I will have to come back to you on that one. Yes, sorry, op is just oppositely. There we go. Full stop, full stop. Okay. So, Advik, that's a good question. So a molecule, actually, we'll talk about molecules in a moment, okay? But you're right, a molecule is kind of a discrete um, substance. So, for example, water molecules are made up of one oxygen and two hydrogens, and that's it. Whereas when we have a lattice structure, even though our formula for sodium chloride is NaCl, it's not just one sodium and one chloride, it's, moles and moles and moles of them. Okay. So lattice, that's just your 3D structure essentially. Okay. In terms of electrical conductivity, fantastic, Ayan. It's like you could read my mind. How did you do that? Great. So electrical conductivity depends, and there aren't any delocalized electrons, okay? But if a molecule conducting electricity depends on charged particles, and a charged particle could be either ions, so positive and negatively charged, or they could be delocalized electrons. In ionic compounds, there are no delocalized electrons, but there are charged particles, so these ions. Okay, so when solid, no electrical conductivity because the ions cannot move or the ions are in fixed positions. Whereas when molten, which just means melted, so liquid, or aqueous, which means dissolved in water, then yes, because the ions can move and carry charge. I'm writing behind my head. I'm writing behind my head. Let me move myself. Oops. Oh no. How do I move my head? Go away. Go up here. Oh no. Oh no. Hang on. There we go. Okay. Ions can move and carry charge. Okay. Oh my gosh, Twa Twa, you're back. Toy Toy, Twa Twa. It's still one of my favorites. Okay. So Virali molten just means melted. It just sounds nicer. Okay, I'm glad. Please don't leave me. Okay, so if you melt your solid to become a liquid, so now when our ionic compound is molten or aqueous, instead of the ions all being stuck together, they are now free flowing. Okay, aqueous means dissolved in water. And most, well, I wouldn't even say most, a lot of ionic compounds are soluble in water. And when you put them in water, the ions split up into the individual ions. Okay? Are we okay here? Are we ready to move on? No, do not put delocalized electrons. There are no delocalized electrons. Delocalized electrons means that there are free-flowing electrons. So electrons that don't just belong to one particular place, they're able to move around. There are no delocalized electrons here. There are ions. And when solid, those ions are all stuck together, so they're fixed. But if you melt it down or dissolve it in water, then the ions can move around. And when the ions can move around, then we can get a current. That's what I mean. Physics, a current. Okay, electrostatic forces is essentially a fancy way of saying positive attracted to negative, right? Like electro, like positive and negative charges, and static just means still. Okay. I can indeed. Where can I write that's not behind my head? Let's go. I'll just shift a little bit over here. Oopsie daisy. Aqueous equals dissolved in water. Okay. Oh my gosh, I did say malted. It's because I was thinking, I was saying melted while I was writing molten. Thank you. Thank you so much. How embarrassing. Molten. Molten. Okay. Jude, there are two papers for chemistry, and we'll cover in this year 11 course. Again, we will cover all of the content for the whole course, but we'll start by reviewing the old stuff, then we'll teach the new stuff, and then we'll revise everything with lots of exam technique. Okay. Ashal, so I answered electrostatic. That just means positive attracted to negative. Okay. Again, MK, you can Google it. Literally Google Edexcel to AQA GCSE, and it's the first thing that comes up. Okay. Let's move over to covalent compounds. I'm going to change this word here. Could you please change it in your work pack as well, please? I think I did this also in summer school. Let's change this to simple molecules. Okay. Dex, I don't teach in a real school anymore. I used to. Oh, let me move my face back down. I used to. Oh my gosh, I did the same thing again. But now I work for my EdSpace. Come down here. Oh, it's perfect. Okay, I changed it for you and forgot to change it for myself. Okay, fine. So, when we have covalent bonding, there are two types of structures that we can have. Highland, that's absolutely fine, whatever's easier for you, as long as you're able to follow. So, most covalent compounds that we come across are simple molecules, which just like water or ammonia or carbon dioxide, it's where we have just a few atoms covalently bonded together. Okay? So when we have simple molecules, even though there are covalent bonds within the molecules, what holds these molecules together in its structure? Some of you were saying it before, but this is now the only time that you should use this word. What holds simple molecules together? Not delocalized electrons, not intramolecular. Afia, absolutely. Great. Inter, fantastic. So held together by weak intermolecular forces, bruv. Okay. So in terms of melting point slash boiling point, we know that they must have low melting and boiling points because as soon as you see weak, then that means that only a small amount of energy. Oh, yes, hydrogen bonds, but we don't talk about hydrogen bonds. Actually, no, we kind of do in biology, biochem. Small amount of energy needed to overcome them or break them. Oh, some good questions in the chat. Let me just have a moment and read them. Madian, delocalized means so local, like if you're local to somewhere, then you're from that place. Okay, so something that is delocalized means that it doesn't belong to any particular place, right? So in metals, and we'll just take a tiny little detour, we have our positive ions and then we have our delocalized electrons because those delocalized electrons don't belong to any particular ion, they're just moving around. Okay. Yes, we will do crude oil and hydrocarbons, absolutely. Okay. Let's see. I just want to make sure I'm answering these questions. Difference between intermolecular and electrostatic force. Ayan, that's a really good question. And in fact, in not to confuse you, but intermolecular forces are electrostatic forces of attraction as well. Okay. But when it comes to bonding, like ionic bonding, covalent bonding, that's when we're sharing electrons essentially, or we're transferring, we've got a positive charge and a negative charge, and they're attracted together. But when it comes to intermolecular forces, these forces are still between positive and negative things, but they're just a lot weaker. So they don't count as bonds. So we are not, and I think somebody said it earlier, we're not going to use the word bond when we're talking about when we're talking about intermolecular forces. Okay. Khadija, there will be lots and lots of revision. Okay. The words say on the last sentence, small amount of energy needed to overcome them. So to overcome the intermolecular forces. Or you could say to break them. But typically, when we're talking about intermolecular forces, I like to think about overcoming those forces. We talk about bonds, Jamie, if we're talking about ionic bonds or covalent bonds being broken. Okay, intermolecular forces are not bonds. Okay, Ishmael, the link for the work pack should be in the description for this video. It is, there we go, Louis Bond, Louis Bond. So yes, these not that they can be broken, not that they can be broken quickly, more the amount of energy that's needed to break them is very low. Okay, so they have low melting points and boiling points. Because melting and boiling point is directly linked to the amount of energy needed to break a bond or a force. Okay, we're not going to cover metallic bonding today in the interest of time, but when we come back to our metals later on for revision, we'll talk about metallic bonding again. I want to focus on ionic and covalent because we see that more um, in the next couple of lessons that we're doing. Okay, I hope we'll have time. Let's keep going. Okay, now so the timetable you can get on Teachfloor, so on the app. Will I help you get your 5? That's the plan. Maybe even more than that. Okay. Giant molecules. Can you give me some examples of giant covalent structures that we need to know about? Okay. Blurry, the lesson is an hour. Lovely. Diamond. Fullerene. Oh, I'm not going to put fullerene in there. Graphite. Lovely. Lots of you are saying graphene. The chat is moving quickly. Fantastic. I saw silicon dioxide. And I'll take one more. Not buckyballs. Buckminster fullerene is actually simple, but Donald has got it. Absolutely. Nanotubes. Great. Satoru as well. Okay. Nanotubes, Queen Rose, you're absolutely right, are also fullerenes. Let's talk about the differences between some of these in the next couple of slides. Let's talk about them. Actually, no, but very, very quickly first, a question I get asked a lot is, how do you know whether it's going to be a simple molecule or whether it's going to have a giant structure? And the answer is, you just know. The giant examples are the ones here, and simple molecules will be everything else, okay? Unless they tell you in the question, okay? So, really, really common to be asked about differences between some of these allotropes of carbon, so different types of carbon. So, for example, graphite and diamond. So, in the chat, can you give me some similarities between graphite and diamond? Lorenzo, yes, water is a simple molecule. Diamond has a high melting point, but what about graphite? Does graphite have a high melting point? Okay, yes, both made out of carbon. I can put that in the middle. They both have high melting point. What else? Ooh, only graphite conducts electricity. Fantastic. What else do we have? They're both giant. Excellent. They both have strong bonds. What type of strong bonds? Strong covalent bonds. Ooh, not quite. So they don't both have layers. Only graphite has layers. With diamond, every carbon is connected. Fantastic. Tetrahedral structures, Satoru. Mahi, amazing. Graphite, 3 bonds per carbon atom, but diamond makes 4 bonds. What else do we have? Why is it covalent? They're covalent because carbon is a non-metal. And so when it forms bonds, it's going to be covalent bonds. They're going to share electrons. Okay? Both are absolutely solids. What else do we have? Lovely, both have giant lattice structures. What about some of the properties? Okay, yes. Ooh, lustrous. I like that word. Graphite is soft, fantastic. And slippery. Oh, that says tetrahedral. Who said that? Stanley, it says tetrahedral. Lovely, diamond is hard. Graphite, I wouldn't say malleable, we would say soft and slippery. And you're absolutely right, Tifemi, soft and slippery. Let's start to put our explanations in here. I'm going to do it with a different color. Oh yeah, graphite can be used as a lubricant. Okay, let's start to explain some of these. So, why does graphite conduct electricity? Well, it conducts electricity because, and this is what you were all waiting for, it has, do I have it? Okay, no, I don't have it on the next slide. Graphite has delocalized electrons. Fantastic. Iron, absolutely soft and slippery because between the layers, what holds the layers of graphite together? So graphite is made up of out of these hexagonal sheets, right? And there are strong covalent bonds between these carbons, but from one layer to another layer, those layers, fantastic, are held together by, excuse my terrible graphite, intermolecular forces. Great. So weak intermolecular forces between layers. I'm going out of my Venn diagram, but that's only because I had to write so large. Okay, therefore, the layers can slide over each other. Okay, let's have a look. Do we have any more questions in the chat? No, I think okay, we're doing great. Tetrahedral, somebody asked earlier. Tetrahedral just means, if I draw it out here, diamond, each carbon is bonded to 4 other carbon atoms, and that structure is called tetrahedral. It's called a tetrahedron. Okay, can we keep going? What about graphene? That's on the next slide. So delocalized electrons, okay, let's explain why there are delocalized electrons. If we come down to here, remember, carbon can make how many bonds? Again, let's bring the chat back onto topics that I can see the questions here. Fantastic. So carbon can make 4 bonds, right? So 4 electrons in its outer shell. So can make 4 bonds. So share these with other things. And in diamond and in graphite, shared with 3 other carbons. So then what happens to this electron here? Well, that electron gets delocalized, which means essentially it falls off of the carbon and instead just gets to swim around free between the layers. Okay. And because these are so not free flowing ions, free flowing electrons. An ion is a charged particle like a Na plus or a Cl minus, as opposed to a single electron. Okay. Because of these delocalized electrons, these can move and so they can carry charge. We know that carbon can make 4 bonds because it's in group 4. So there are 4 electrons in its outer shell. Okay. Okay. So again, I'm just deleting a couple of things. Any other questions before we move on? I think Samuel asked, what did I say? What does the word say under diamonds? Tetrahedral. C atom means carbon atom. The 3 dots Isabel does mean therefore. Okay. If you don't understand a topic after you explain it, what should you do? Try the homework and then go through the video solutions to see if that helps. If that still doesn't help, then talk to your mentor if you have one. And if that still doesn't help, then rewatch the video. If that still doesn't help, then in a later lesson, ask it in the chat and then I'll try and get there as well. Okay? So what makes a structure giant? A structure is giant if it's not just making one bond, but it's extending out in 3 dimensions. Okay. If you contact your the customer success, there we go. Naima just let you know your mentors will contact you by the end of the week. Okay. Katie, the video will be the marking for the homework, but you can also talk to your mentor if you're not quite sure if you should give yourself the mark. Okay. Let's talk about our other allotropes of carbon quite briefly. So we mentioned these already early on. I'm actually going to start with the one in the middle. What's the one in the middle? Okay, the one in the middle, lovely Sharifa, is graphene. The one on the left, these are our nanotubes. And then on the right, this is our Buckminster fullerene or buckyballs. Great. Now, graphene is just essentially a single layer of graphite. And so it has very similar properties to graphite in that it also has a high melting point, can also conduct electricity. The table, what table? Do you have a table and I don't have a table? That's fine. The one on the right, Buckminster. Let me hang on. There we go. Okay. So a single layer of graphite absolutely is graphene. Okay. Now, when it comes to Buckminster fullerene actually has a simple molecular structure. And that's because these balls, these buckyballs are discrete. So Tifemi, you're absolutely right. They are made up of 60 carbon atoms, so C60. Whereas these giant structures, they don't have a particular number. So for diamond, you don't know how many carbon atoms are in diamond. It technically just keeps going on and on and on and on. Whereas for Buckminster fullerene, there are 60 of them, and then those are held to other Buckminster fullerene, pretend that's another one, through intermolecular forces. Under the third image, it says Buckminster fullerene, and then it says simple molecular. Lithme and allotrope just means different forms of the same thing. So carbon is one element, but carbon can exist in different structures. So it can exist as diamond, graphite, graphene, nanotubes, Buckminster fullerene. So all of those we just say are allotropes of carbon. Okay. And then for nanotubes, these are also fullerene, so they have a similar structure. If you look at graphene, nanotubes are just like graphene, but just folded into hollow tubes. Okay, and so they will also have similar properties to graphene. They will have high melting point, fantastic. Then they will also be able to conduct electricity, which is why we see them in a lot of nanotechnology. Okay, you're absolutely right. Isotopes are for atomic structure. Okay, we've got 10 more minutes, so I think we should keep it pushing. They do, Jude, fantastic, have high tensile strength. Okay, so let's take a moment to make sure that we can identify what sort of structure we have. So we'll go along, each one, let me know which structure. So for iodine, what structure will we have? Ionic, simple molecular, or giant covalent? Feel free to just put the like acronym in there. Absolutely, Tifemi, Jmeet, simple, molecular. A fullerene is just a hollow structure. So sort of like graphene, where we've got our hexagons, but for Buckminster fullerene, it's just folded into a hollow ball, and for nanotubes, folded into tubes. Okay. NH3, Mahad, is not ionic. Nitrogen and hydrogen are both non-metals, which means that it must be covalent bonding. And then when it comes to covalent bonding, we've got two options, simple molecular or giant covalent. We know our giant covalent examples, and NH3 is not one of those, so it must be simple molecular. Okay, so these are the three structure types. Um, No, so the lesson is from 8 to 9. Today, we had our little intro at the beginning, but in future lessons, of course, we won't need to do that intro. As soon as the lesson starts at 8, we just go straight into the content. Okay? NaCl, Mahad, I agree, ionic, because we have a metal and a non-metal. C60, that's our Buckminster fullerene. So that's one where we think it might be giant covalent, but it's actually simple molecular. Lithmi, I don't know what you mean. How do I know what? I need a longer question. How do I know what? For graphite, absolutely fantastic, giant covalent. And for CH2O, I've never seen, I mean, I've seen it before, but even if you haven't seen it before, you can still figure it out. Okay. Remember, for ionic, we need a metal and a non-metal. For simple molecular, that's just non-metals. And for giant covalent, that's also non-metals, but specific examples that we know. So if it's not one of the specific examples that we know, like diamond or graphite or graphene, then it's going to be simple molecular. Okay, so CH2O, you're absolutely right, must be simple molecular because all of these are non-metals, so must be covalent bonding, but it's not one of the giant covalent ones that we have learned. Okay, simple molecular and giant covalent are both covalent bonding. It's just different structures. Yvette, next lesson is on writing equations, so don't you worry. And there'll be lots and lots. Honestly, you might get sick of it. There's going to be lots of writing equation practice. Okay, let's keep going. Just by looking at the structure, we can also determine what structure type it has. How do I know? Katie, I just explained that. How do we know which structure it is? If it's a metal and a non-metal, has to be ionic. If it's non-metals, then it's going to be simple molecular or giant covalent. And we know particular examples of giant covalent. So if it's not one of those examples, it has to be simple molecular. Okay, let's come back here. Substance A, well, we can see we've got oppositely charged ions, so the green and the purple in a giant lattice. So you're right, that must be ionic. For B, Say that would be metallic bonding or alloys. Substance B, absolute. So careful. There's no such thing as simple covalent, simple molecular, absolutely, or simple molecules. And then substance C, absolutely, Afia, giant, covalent. And specifically, can anyone spot which giant covalent structure this is? This isn't graphite. It looks like diamond, but we've got two different elements. We've got red and yellow, so it can't be diamond. What must it be? What's the other one that looks just like diamond? Tazeen has got it. Lovely. This is silicon dioxide. If this was diamond, everything would be the same color because it would be an element. Fantastic. Okay. Last 5 minutes for us to practice how we explain. How do I know which one is which? Ultimately, we need to be able to recognize them, right? So when it comes to ionic, we're looking for like a cubic structure with different colors that show oppositely charged ions. For simple molecules, we're looking for individual molecules that are separate from each other. And for giant, we should be able to recognize the giant examples. Okay? Let's look at how we structure our answers. We've actually kind of covered this already earlier, but just to make sure it's cemented, if we're asked to explain why a substance has a high melting point or a low melting point, then we need to consider these 3 bullet points in our answer. Okay, so we need to answer what type of structure is it? What holds that structure together, and are those weak or strong? And so how much energy is needed to overcome them? Lamisa is way ahead of us. One piece on top, silicon dioxide is not an allotrope of carbon. It's a giant covalent compound, but it's not an allotrope of carbon. Okay? So for this question, explain why sodium chloride has a high melting point. First thing to identify, what type of structure does it have? Now, because here we have a metal and a non-metal, we know that the structure must be ionic, but specifically giant ionic. Okay, so we'll start by saying sodium chloride has a giant ionic structure, or giant ionic lattice structure, even better. Okay, what holds a giant ionic lattice structure together? Well, it's ionic bonds, but let's define them. Coming back to our definition of ionic bonds are, so it's held together by, lovely, even more electrostatic forces of attraction between, so strong electrostatic forces of attraction between oppositely charged ions. In the interest of time, I'm just going to write op. And then we link that to energy. So how much energy is needed to break those bonds? Lovely, Uyan. So a large amount of energy required to break the bonds. Okay, so, and that is our structure every single time. So let's do, I know we've only got 1 minute, but in note form, we can try the rest. Okay, so the first hurdle is identifying the structure. And once we've identified the structure, the rest of it kind of comes naturally. So explain why NH3 has a low boiling point. Again, What type of structure does NH3 have? Again, it's non-metals, so must be covalent bonding. Between our covalent bonding could be simple molecular or giant covalent, but it's not one of our giant covalent examples, so simple molecular. So we would say NH3 has a simple molecular structure. Answering our second question, not simple covalent, simple molecular. What holds a simple molecular structure together? So held together by weak, lovely J-meat, intermolecular forces. And then so answering that last question, how much energy would be needed to break them? A small amount. Okay. It's 9 o'clock. Should we do one? We'll do one more. We'll do number 3. Okay. Again, we're following the same structure. For diamond, what type of structure does diamond have? So I am not less energy because we're not comparing it to anything, just a small amount. If we were comparing it to something else, then we'd say more or less. Okay. So you're right, diamond has a giant covalent lattice structure held together by not intermolecular forces. Intermolecular forces we only see in simple molecules. In giant covalent structures, those are held together by covalent bonds. So held together by strong covalent bonds. Therefore, how much energy is needed to break those bonds? Oops, oh my gosh. A large amount, or a lot, yes, of energy required to break those bonds. Okay, so first step, identify the structure. Remember, metal and non-metal means ionic, non-metals, covalent, and within covalent, it's either going to be simple molecular or giant covalent. Okay, the lesson has ended. Okay, I think there's there's actually one question left, but it's very, very similar to a question that's in the homework. So once you've done the homework and marked it, it's basically the same as that last question. Okay. And we're going to come back to this again in our review at the end of the topic, the module. Okay. Oh, that was a lot. Really well done. Okay. From tomorrow, we're going into some mathsy stuff. Actually, no, we're going into balancing equations tomorrow, so get ready for that. Periodic tables at the ready. Not tomorrow. When is our next lesson? Whenever our next lesson is. That's what we'll be doing. Okay. Have a wonderful evening. Don't stay up too late. And I'll see you very, 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 very soon. Okay. Amazing. Ryan, super quickly for 2, I'm just going to say what type of structure it is. MgCl2, we have a metal and we have a non-metal, so must be ionic. So it would just be giant ionic structure held together by large amount of energy. So basically the same answer as for sodium chloride. Okay, don't forget this lesson is recorded. So if you want to go through it at half speed, pause at certain parts to make sure that you've really, really, really got it, then please do. And don't forget, we're going to come back to this later on in the topic when we do our review of the review. Okay, trust me, so much time for revision. So we're going to keep going. How do you know if it's a metal? By looking at the periodic table, Michelle. So everything over there is a metal, and then these are our non-metals. Okay, lovely. I'm glad you enjoyed. Take a break, take a rest, have a nap, or just go to bed. Okay, and I'll see you soon. Bye, bye, bye.